So please let me know if the screen is visible.
Yes, sir. Your screen is visible. It's visible.
Great option airport.
Yeah.
Let me put it to the full screen. Yeah, is it still visible on the full screen mode?
Still, yeah, it's visible, sir.
Okay. So our budding engineers from Srinagar College and other colleges, the faculty, the other audience today, let me tell you that bridges have one level of difference compared to buildings is that bridges are in public limelight always. They are infrastructure projects. We have to be more sure about the correctness, about the accuracy, especially when we design bridges, for the reason that if anything goes wrong, it is the public at large that is affected. And if something is very nice, it is you who get the appreciation from the politicians, from the public, and from everybody. So it is like a thing that you always see. Good side of it, bad side of it. It's very important. The difference basically between bridges and buildings is that in buildings, we may have 1,000 beams. In bridge, we may have only one beam. But in that one beam of bridge, we go into lots and lots of details of it, including creep, shrinkage, expansions, contractions. All those things may not be so carefully or so much in detail analyzed in the case of buildings. And there we have, as I said, hundreds of thousands of beams and slabs and all that. So there is some difference that we go into a lot of intricacy when it comes to the bridges. And my request to Professor Pusari and Shraddha is that anytime I'm not audible, anytime I'm not visible, when I say my screen, please let me know and interrupt me and let me know.
Sure,
Because
sir,
Zephyr
sure.
is available on a standby. All right. So first, friends, let us see the basic classification of bridges as per Indian Roads Congress codes. Culverts have a span up to 6 meters. Small bridges have a span from 6 to 12 meters. Minor bridges, it is found when the length of the bridge is 12 to 60 meters, and major bridges are above 60 meters of total length. The spans may be smaller. In fact, in the small bridges also, it is a length which is a criteria, not really the span. From 6 to 12 meter of length of the bridge will be called small bridge. Okay, what are the basic types of bridge superstructures these days? These days means as of now, latest. In the past, not so common now, but we do have some slab bridges, which are RCC or PSC slab, which is like a solid slab, as like in a building. You have a slab which may span from, let's say, 5 to 10 meters in the case of RCC, maybe 10 to 15 meters in the case of pre-stressed concrete. But somebody may wonder why not more than that. You can have more than that, but the cost goes up. Material quantities, they increase heavily. Earthquake also increases because the initial mass increases. So it's because of those practical reasons, we'll go for a solid slab only for spans between about 5 meters to 15 meters, RCC or pre-stressed concrete. PSC means pre-stressed concrete. If we have spans larger than that, and if we still want a neat and clean looking slab, then we will go for something called voided slab superstructure, which may be reinforced concrete or it may be pre-stressed concrete. We will see some pictures of all these. If we have larger spans than 15 or 20 meters, then we can go for cast in situ T-girder bridge. Cast in situ is one category, where you really put a shutter and you cast, which may have RCC T-beams or it may have pre-stressed concrete T-beam slab together. Alternatively, it can be precast girder topped with RCC slab deck. The precast beam may be in RCC or pre-stressed concrete, but the slab will be typically in reinforced concrete, RCC. We can have single or multi-cell box girder bridges, which again can be in RCC or PSC. We can have a cantilever construction bridge where we cannot put shuttering and the spans are large. So when the shuttering cannot be placed, the span is large, we have cantilever construction. We will see some pictures as to how they are built up and constructed. Um, if you're aesthetic lover, then we can have arch bridge for larger spans, especially. They look very good. They can be in reinforced concrete or steel. We may have integral bridge. Integral means it is something like a building frame that the superstructure is monolithically connected to the bridge without any pier cap and bearings. That becomes an integral bridge, which can also be RCC or PSC. We can have steel through girder bridge, like a truss bridge, which is all open web structure, or we can have steel plate girder bridge, which is a solid plate having a top web, a top flange, bottom flange, and a plate with the stiffeners, etc. The newer technologies over the last 20, 30 years or 40 years now are precast segmental bridge to give us a speed, and it's still a good quality because their precast concrete segments are manufactured in a casting yard. That's a factory kind of a condition. We can have precast segmental spine wing bridge. In the spine wing bridge, again, we will see pictures. We have main spine, that's a segmental structure of the middle. And on the sides, we have other set of precast segments transversely pre-stressing the entire thing. We can have extra dose bridge. Now, here we talk of cable supported bridges. In cable supported bridges, there are three categories. One is extra dosed, which we'll see what it means. Other is cable stayed, which you mostly hear. And third is suspension bridge for larger and larger spans. So if we talk of the span range, extra dose bridge is good for about 50 meters to 200 meter span. Cable stayed bridge is good for about 200 meters to 1000 or 1200 meter span. Suspension bridge is good for anywhere around 500 meters to 2000 meter span. And today we have a bridge with a clear span of 2 kilometers or 2000 meters. So this is a simple cast in situ T-section bridge. If you remove the webs from here, it becomes a slab bridge. This is precast concrete below, or let me put it to options. Yes. If you see below, it's a precast pre-stressed concrete beams, topped with in-situ depth slab, as I said, always in-situ depth slab. And this is a steel beam bridge where you have eye girders or you have plate girders topped with RCC deck slab. So this is just a picture of a 40 meter span bridge wherein the pre-stressed girders are at a spacing of 2 meters transversely, and longitudinally they have a span which is each one is 40 meters in the base here. Typically a box girder bridge would look something like this. It has a deck slab, it has webs, and it has bottom slab. Top and bottom slab, we may also call them flanges. Top flange, bottom slab. Side ones are the webs. Now what happens is that this structure is not a solid structure like in the case of slab or T. This structure is cellular structure. You know, so it gives you a larger I value, Z value at a lesser concrete quantity. It becomes more efficient, but there is certain punishment we have to take, that is to make it strong enough or rigid enough against its own buckling, internal buckling and distortions of this shape. Once we do that, this is very efficient, and lots of structures are constructed with this technology. They can be single cell box, they can be multiple cell box, or whatever. Yeah, they can be all kinds. Multiple cell, when I say, in multiple cell box, we have more such webs. If there are 3 webs, third web is here, then this becomes a 2 cell box. If there are more than that, then it becomes 3 cell, 4 cell, 5 cell box, depending on the width of the C or in pieces. All right. Now we have voided slab. In voided slab, what happens is very similar to solid slab, or whatever shape we choose. For aesthetics, we choose a lip shape, and we create holes like this to reduce the concrete quantity and the weight of the structure with the help of something called void formers. White formers I will show you. Yeah, these are the white formers. We have these metallic pipe type of thing sealed at the ends like this, and they are placed in the concrete shuttering after placing the reinforcement and other things, and they are held tight with the help of some anchors so that they don't float when the concrete is wet, because concrete exerts a hydrostatic pressure. And once we do all this, pour the concrete, pre-stress if there's a pre-stressing, or just RCC, whatever it is, it becomes a lighter structure by approximately 20% of weight for the given depth. This is a multi-cell box. It's a twin cell box wherein you have a web, another web at an inclined plane for athletics, and also to reduce the slab thickness, top slab thickness, and it becomes a two-cell box. This is in fact a picture of a precast segment for a project wherein you see the shear keys here. Just remember, these are shear keys of precast segments, and we will be discussing the shear key also in a while. Now, when we say low bedded trailer is required. It should not be too high, because if it's high, the trailer may topple during taking turns on the roads. So we try to create low bedded trailer. Typically, a low bedded trailer will have a height from the ground till this bed of 1 meter. That's a low bedded trailer. Now, this is cantilever construction. In this, as I said, like in this case, each of these piers that you see is height of a Qutub Minar, 70 meters. Now, if I start providing shuttering or staging of the 70-meter height, the staging will go away, fly away with the wind towards a valley, and such a tall shutter will have its own, staging will have its own stability problems. So what we do, we construct some part here over the pier with the shuttering as in situ. Thereafter, we erect this kind of a formwork traveler, we call it, for a cantilever construction. One on the right side, one on the left side. With that formwork traveler, we cast in situ or precast, whatever we do, one segment of normally about 3 meters. It can be slightly more, slightly less. And then we pre-stress it. Thereafter, we cast the next segment by moving the formwork traveler away and away from the center, and we do the pre-stretching at every stage. Once it reaches the center, then we do something like this, that we put a hanging shutter. On this shutter, we put reinforcement, pour concrete, and the job done. Come to the aesthetic shapes, that is arch. In the case of arch, we have arches that look something like this, which has verticals to support a deck on which you move. It can be a case like this, where you have an arch like this, maybe flatter, maybe deeper, and you have a deck where you move. That means there are two parallel arches, and between the two arches, there are two of these horizontals on which you have a slab to traffic to run, or you have a semi-through kind of an arch where the arch suspends a deck, but also it has a short arch piece. Now, about the arch, if you have studied in your colleges, you will know that arch takes the vertical loads through a flow process of forces or the stresses as membrane forces. Membrane means it forms two components of the vertical load along this and perpendicular to this, and they start getting balanced with each other. So finally, what is left over in the arch rib is only compression, axial compression. And as a result, arch becomes lighter, cheaper, and of course aesthetic at the same time. But the punishment of the shape comes at one place, and that is at this point and this point, because it generates a high amount of force horizontally and vertically, of course. So a resultant force that is something like this in this direction, or something like this in that direction, for which a strong foundation has to be made to cater to mainly the horizontal force. And that is very easily solved in the second case, that this deck acts as a tension member, axial tension, so that horizontal force that goes like this and outward on the other side like this is catered to by this tension the help of this that we have. This is a structure. It is on the border of in between Singapore and Malaysia. A series of arches. What they have done is made the central arch large in span, and as you go towards the shore, and there are 20, 30 arches, it goes on reducing in the span. I know that the designers have to work harder to design so many spans of different span length, but the advantage is aesthetic. But aesthetically looks very nice to have varying span lengths, lesser towards shore and more towards middle. Uh, this is an arch bridge that we designed and was constructed by a contractor in Himachal Pradesh, where it's a span of 120 meters. It has these things. It has this deck hanging from this, and this river is so turbulent that no shuttering could be placed. So this entire arch was constructed by cantilever construction method from either side. And once the arch was completed, then suspenders were put, which are permanent suspender to suspend the shutter, and then cast this concrete and remove the shutter. The suspenders remain. Look at very aesthetical masterpiece. It's a bridge in UK, Gateshead Millennium Bridge, over River Tyne with a span of 105 meters. It has been designed and constructed in such a way that the entire manufacturing of this arch, which is a total weight of 800 tons of steel, was done off the shore somewhere else. The entire thing was brought on the barges, on a barge of 3,200 ton capacity to this place and fixed here with the help of these hydraulic pivots that you see at each of the ends. Now the advantage is when hydraulic pivots, mind you, when ships have to pass, then they lift the arch up, and when the ships have gone, they drop it back and now pedestrians can move. And of course, it looks excellent. During the night, it looked like a necklace of a princess with the lights reflecting from the water. Now we come to another form that we discussed, integral bridge. If you have a structure, this is actually Kuala Lumpur International Airport, which we designed this bridge for a long time back. If you have a structure which is curved like this, and if you put this structure on bearings, two bearings, transversely two, then the structure being so sharply curved, it will fail in stability. If it topple, bearings will go into tension. So to avoid that, we have made these piers integral to the structure without any pier cap and bearing. It looks aesthetically also good. It avoids bearings, which are sometimes a source of problems, and it becomes stable as we want it to be. And this is a ramp, through which you go to the airport before you alight your car. Look at another interesting integral bridge. Now in this case, the piers, let's say if it's a single pier supposing, is not at 90 degrees. It is at 20 degrees. So pier is almost in the direction of the bridge, just missing it by 20 degrees. The skew, as we call it, is 70 degrees as opposed to 0. Now in these cases, when a bridge rests on the pier and bearings, and if it does, it will have the tendency of lifting up, not toppling fully, but lifting up and creating problems in the bearing forces going negative. And other bearings will have excessive vertical load, because this will be a balancing out situation. So we have made it integral with the help of the multiple piers, 5 numbers of piers at each pier location. So because the skew was a must due to traffic reasons. Other thing we discovered is steel through girder bridge. That means open web bridge or a truss kind of a bridge. So this is the shape of a truss kind of a bridge, very similar to what you design as trusses in your colleges or whatever for buildings, etc. Sometimes we design even verandial girders. So this is not a verandial girder, but this is a truss bridge. It can have a large depth. This depth may be nearly about 1/10 or 1/12 or 1/15 of the span. Then you have bracings to take the shear. Otherwise, you have a steel plate girder. In the steel plate girder, you have solid plate with stiffeners bottom flange, top flange, and on top of that you put a concrete slab which acts as a deck slab. Now in this, the advantage is that this looks neater, it looks cleaner, it looks better aesthetically, but it also cannot take too big spans. Truss girder could take even a span of 200 meters for that matter, but a steel plate girder will not be able to be designed for more than 50, 60, 70 or 80 meters. That's about the maximum. Beyond that, it becomes too expensive, too bulky, too wild. All right. Now we talk of precast segmental bridges. This is what we see day in and day out in our practical lives when we pass through the cities for metro construction, for flyovers and all that. And in your Pune also you have several of them. Mr. Lema is in charge of several of the precast segmental railway bridges, metro bridges. Right. So in precast segmental, what happens that we cast concrete segments in a casting yard. In the process, the quality is also better because we have a better control in the casting yard. It's like a factory in a way, producing the concrete segments for you. And then we bring those segments, assemble them for each span at a time. Assembly can be in two ways. One is underslung assembly, wherein you have a launching girder which is below and segments will come on the top of it as you see in the right side picture. And here is a portal that lifts a segment from the trailer, lifts a segment, place it on the launching girder, lift the next one, place it on the launching girder, assemble all the segments. After that, we apply epoxy resin, which is epoxy glue, eraldite type of a thing, more like eraldite only, and then you put some pre-stretching, etc. The other method is to go for overhead. In overhead, what you do, you have a overhead launching girder, and this launching girder is you suspend the segments with the help of wire ropes. You suspend the segments of a span of segments. Thereafter, you do the same process of epoxy again in place. This is one picture taken from a DMRC project done about 15, 17 years ago. We use overhead launching system because segmental, you see the joints every now and then. So each segment is about 2.5 to 3 meters long in this case. And at the joint, that epoxy resin is applied. Now, enhanced form of precast segmental is even transversely also precast segments. This is an example from the problem they had was the width of the road there amidst the traffic that is running is not so much to handle a 60-meter wide segment, which is 3 meters long, of course, on those roads for it to travel from casting yard to the axle site. So they decided to limit the width of the segment to only as much, which is called spine, which I think somebody mentioned just now about spine. And after all these segments of the spine, which is 3 meters each and peer to peer, they're all placed, pre-stressed. Thereafter, you bring in these transfers, these wings we call it, the spine wing construction. So these wings, bring them in through the cranes, and after applying concrete stitch or epoxy stitch, you put a transverse pre-stress for it to be one. This is the epoxy application I was talking about. It is simply hand applied. It's a two-component epoxy, resin and hardener. Resin is light in color, hardener is dark in color. They are mixed in certain proportion. They are mixed into a agitating rotor with a speed of 400 RPM for about 1 or 2 minutes, and thereafter applied. And within 20 minutes, you have to apply, and there are certain restrictions. And within 60 minutes, you have to put a pre-stressing. So you have to design your systems accordingly. Once you've applied the epoxy, you first apply a temporary pre-stress in such a way that it can give you more or less a constant stress, compressive stress across the joint where you have applied the epoxy of zero point 0.3 MPa, zero point 0.3 MPa, and keep it for 24 hours. I mean, with the help of this kind of systems, it's a temporary. And thereafter, you put the internal permanent pre-stress, stress it, that is a permanent pre-stress, which may be as high as about 30, 40, or 50 times of what I said, 0.3 MPa, and remove these temporary pre-stressing arrangements at that stage. Now come to the cable supported bridges. In cable supported, the first category for smaller spans to the tune of 50 meters to 200 meters. In fact, now we are preparing a code also on this, Indian code. Extra dose bridge can be had. In the extra dose bridge, height of this small pylon that you see is about 10 to 12% of the main span. If the span is 100 meters, this will be about 10, 12 meters. That's the height. And these cables which you see, they look like suspenders, but actually these are not suspending cables, or these are not cable stayed cables. They are more like internal pre-stressing has gone outside. So these are like pre-stressing cables. That's a technical difference. The second one is cable stayed. In cable stayed, you can have spans anywhere between 200 to 1200 meters so far. The pylon height is about 15 to 20%, even 25% of the span. Like in this case, the span is 856 meters. So pylon height is also a good number. Is I think 200 meter or something is the height of this pylon. Now here the difference. Each of these cables that you see, they become elements to suspend or to lift every part of its superstructure or its own share of the superstructure. And since they have to support these, the pylon has to be taller so that the cable have an angle closer to vertical and not flat, unlike in the case of extra dose bridge. So this is cable stayed. Typically, both in this type and the other type, if it's a three-span structure, the end span will be about half of the middle span, or 60%. Here also it will be about 50 to 60% of the main span. For example, if this is 856, the span from here till where the cables are going will be approximately half of 856 meters. How it is constructed is very simple. It's a cantilever construction where you first construct the pylon on the foundations. You then place here, if you see, you place one segment. If it's precast, then precast. If it's steel, then steel. If it's in situ, then in situ, using forward traveler in that case. Place one segment, put the cable, place another segment, put the cable symmetrically on the other side also. And you can do simultaneous construction of the other pylon till such time it hugs each other, and there you put the central buoy. Suspension bridge is a completely different technology and is good for large span bridges. In suspension bridges, what we do is we put one main set of cable, which is a suspension cable, and this main cable supports auxiliary vertical cables to suspend this bridge. So here what happens is that this pylon becomes about 16% or so of the main span in terms of height. There's one advantage. Secondly, the difference is that this cable that we see, the suspension cable, is the main cable that takes the entire load, unlike cable stayed where every cable was taking load, and these auxiliary cables take their share of the deck load. It's very different, and with this technology you can have spans up to 2 kilometers unsupported. So this is an example of that bridge which still holds world record. It was constructed in 1999. It has a steel deck of 35 meters width, a span of 1991 meters precisely. It has 300 meter tall steel pylons, and it is in Kobe state of Japan, called Akashi Kaito. It's actually Akashi state in Kobe of Japan, sorry. And this span is about a kilometer 2 kilometers, and a kilometer. So it's a 4 kilometer long bridge. And the ropes that you see, the cables, they are also 4 kilometers length. They have a weight which is, each one has a weight of 40,000 tons. So the big issue or big challenge for the constructor was how to carry this cable across the seabed in the strait. Strait means narrow and somewhat shallow, not shallow, but narrow stream of water in the sea. So what was done was that a combined power of high capacity helicopters and high capacity barges working in the sea and above, they were pulling these cables from one end to the other end across the seabed. And that's how they could manage to pull the 40,000 tons of weight. Okay, so now we have seen superstructures, we go to foundations. In the foundations, we have open on spread footings, which you must have all seen in your colleges. We have pile foundations, which also you must have heard, and we will see how it looks. We also have something called well foundation. We also have something called caisson foundation. We also have something called micro pile foundation, though these two are not so common in India, but they are also foundation forms. And we have pile rock foundation. Let's go down and see. So open foundation can have a, let's say if it's a annular pier of a bridge, then it can have a shape like this, which can be circular, square, whatever you choose based on the economics, based on the design. It may be horizontal here and inclined thereafter to reduce a concrete quantity. It may have a shape like this. This shape can be, normally suitable when this width is large. Like in this case, it is for a chimney, wherein the width is almost 25 meters. In that case, it makes sense for economics, etc., to taper this also and taper this as well, both the sides. There can be another type when you have a small diameter here, although in this case it is not small, it is 27 meter. But if it's a small diameter like 7, 8 or 10 meters, this can well be flat. It doesn't have to be always tapered. By making it flat in this case, the advantage we got was that the maximum thickness reduced and the reinforcement reduced, even though we have gone with a larger quantity of concrete. And it turned out cheaper in this particular case when we did the analysis. All right, let us see pile foundations, and let me see how many slides I have to cover. Yeah, it's about half more. So, okay. In pile foundation, what happens? You have a hydraulic tool. Usually, we use hydraulic tool. This is hydraulically operated, which can use the shaft to rotate this into the ground, and through the rotation, it picks up the soil, it excavates the soil and picks up through a bucket which you attach to grab the soil out. Likewise, you create a hole in the soil wherein you have to place the reinforcement like this. Interruption. You place a reinforcement, which is you lower the reinforcement, and thereafter you put a tremie. I'll explain what tremie is. And through the tremie, you pour concrete of pipe. Now this pile goes to 20 meters, 30 meters, 40 meters, 60 meters, 80 meters in Cochin we have done, and outside people have done 120 meters pile, deep pile also. They can give you a larger capacity from the soil, which may be weaker or whatever, especially when it is not rock, you do it more commonly. But in your Pune and Nagpur and all these places, metros are mostly made on piles. But where there's a shallower rock up to 6 meters, they go for open foundations on the rock with the high bearing capacity. So these piles, they give capacity through the side bond that you have on the surface, and also they give you a capacity from the end bearing. So end bearing and side friction, side bond between the soil and the concrete, these two give you the capacity of a pipe, which is of course higher. Now other concept, slight refinement I would say of a pile foundation is pile draft. In the pile draft, what happens? We do the analysis of spring, soil structure interaction analysis, wherein you take the soil as spring You take a pile as a very strong spring, and you take this raft as a structural member. Find out the interaction of all this, and you find that about 20% load or so is able to go from this shaft directly to the soil below, and remaining 80 to this pile. So it becomes a piled raft foundation in your analysis. So once you do this, the number of piles are reduced. We also have this Caisson foundation. In this Caisson foundation, it's a technology used in Malaysia, so I'll probably skip this. So it's not done in India. These are micro piles, which are ready-made piles, which are available in 300 millimeter and 600 millimeter diameter. They are usually high-strength concrete, M60 concrete, pre-stressed, and they are available in 12-meter long pieces. You bring in and you hammer it down. It's a compaction pipe. So it gives you a high capacity because you're hammering it down. But let us see more interestingly and more common type of a foundation here, the well foundation. In well foundation, what happens? You make this part, what you see here, curve and cutting edge, on the ground, which is somewhere here. And after that, you start excavating in the inside. I mean, this part means only this, not the bottom plug. So this annular part, which is circular or something, you make it on the ground and you start excavating here. Once you excavate, because of the cell weight, this annular on top of it as steening, which is this, some part of the steening you build with the reinforcement continuing. And now again you excavate here further, this thing starts going down. So likewise it keeps on going down to reach the bottom. And once it reaches the founding level as decided by the soil investigation, then you put this mass concrete, which is M15 concrete, just a mass concrete, no reinforcement. This becomes a bottom plug to give you a foundation whose width is from here to here. So these things are used, and of course you put some sand, etc. for stability, top PCB, top plug, and finally well cap, which is like a pile cap which takes up here. The advantage here is that it can take much larger vertical loads, and also by the virtue of the fact that it has a large Z value, which may be 5 meters, 10 meters, 15 meters. It has a large Z value, say 15 meters diameter, you call it, or 10 meter. It takes a lot of horizontal forces or the bending moments which are created out of the horizontal forces by the side resistance of the soil. So it is like a wide pile foundation where you are kind of inserting into the ground. So this is a picture of sinking of a well, that every time you do some excavation, the well starts sinking, then you cast more steening, then again you excavate inside, well starts sinking, likewise. Okay, now we go to piers. Piers can be, I mean, fish piers. They can be solid, which is what you see in Pune Metro, annular, rectangular, they can be hollow. They can be solid or annular, circular pier, or any other shape, rectangular, circular, or any other shape. Bridge bearings. The elastomeric bearings. Now, bearings are the elements which are placed between superstructure and the pier cap for the load to be transferred to the foundation finally. We have elastomeric bearings, PTC compound bearings, rubber bearing, and mechanical bearing, roller rocker, which railways use more. In elastomeric bearings, you have an elastomer which is fluoroprene and carbon black and few chemicals put together. You make this kind of a sheet. Inside that you have reinforcement, which is mild steel plates. You vulcanize this entire thing at this temperature. You'll have the handout. You can always read it later. I may be rushing fast. And it becomes a slightly softer material than the hardest steel and all that. And elastomeric bearing works very well. It's fairly cheap. It's the cheapest form of bearing. Only thing we should manufacture it properly. The next one is PTFE compound bearing, which is very popular nowadays. In the PTFE compound bearing, we have a bottom plate, which is anchored to the pedestals over the pier cap. We have a top plate, which is anchored to the superstructure here. Anchors are not shown. At the bottom of the top plate, which is mild steel, we have the stainless steel plate also there, Below the stainless, coming onto the side, so we have bottom plate and we have side walls, again circular in path, and we have a piston which is also circular, and we have a elastomeric disc here, which is for transferring the load equally everywhere. Uh, and over the piston that we say, there is a plate which is called saddle plate. In the saddle plate, we have a small recess of 250 millimeters. In that recess, we put polytetrafluoroethylene, white material. The sliding between the top and bottom then takes place between the PTFE and stainless steel that is here. So stainless steel and this mild steel is connected to superstructure, and this PTFE piston and the bottom one that is called cylinder and the elastomeric disc, they are connected to substructure, and the sliding would take place along this mating line. So this is a picture of a pot bearing. Once you open it out, you will see this elastomeric disc, the cylinder with the bottom wall and anchorage gears for the holes for the bolts. On top of the piston, you don't see the bottom side of the piston, but on top of that, you see these polytetrafluoroethylene (PTFE) sheet, which will be coming in contact with the stainless steel on top of it. And so this. Other types of bearings are cylindrical bearing. And cylindrical bearings is not so common in India, let me tell you. You have a rotation like this, which is only in one direction. So more enhanced form has now come, which is spherical bearing. Spherical bearing, yeah. In this, you have a complete circular path. It can rotate in any direction. It can also slide to stainless steel PTFE layer, like in PTFE compound bearings. And this way it works more efficiently. And this bearing is very recent, but it will become very, very common in India now, of late. And I think Mr. Jitendra Rathore is with us. He must be watching all this. From Sandfield. There is another type of bearing, that is disc bearing. These bearings were used first time in India for Worli Bandra ceiling in Mumbai. In this bearing, you have a disc of a material called polyurethane, which is a very high capacity material. For a larger loads, this bearing is suitable because this requires a lesser area to transfer the load because it has a high capacity. In fact, if you go up and see here, elastomeric bearing will take a pressure of about 10 MPa. Pot bearing will take a pressure of about 25 to 30 MPa. And spherical bearing will take a pressure of about 30 to 45, 50 MPa. That is the difference. And this will take even more. I don't know how much. I am not gone into details of what load it can take, but Worli Bandra ceiling bridge being a large one, it is able to take those vertical loads. Now, when it comes to earthquake, in earthquake, what we want is, we want the structure to somehow become flexible so that the natural time period of the structure is more. And for that, we don't want to reduce the structure. So what we do is, we put this kind of high damping rubber as one material, which gives a damping effect and increases the time period of the structure. Or we use low damping rubber with a lead plug, which gives us a larger damping, means pushing the structure back to its position. Or we use just elastomeric bearing, which is a low damping material, which gives an enhancement of the natural time period of the structure, thereby reducing the earthquake forces experienced by the structure, even though the structure may be heavy. Then I talked about mechanical bearings. These are more used in railways, less now in highway bridges. We have rollers, we have a saddle plate, we have a top plate, we have a bottom plate. This is anchored to substructure, this is anchored to superstructure, and this acts by movement. Okay, now come to expansion points. Where you have two adjoining spans provided with the gap, you can't have this gap permanently because you want the traffic to move on a smooth surface. So this expansion joint transits between the two adjoining surfaces of the deck slab of a bridge. So we have slab seal type, single strip seal expansion joint, modular strip seal, finger type, compression seal, and we'll see each one of them. This is the most common expansion joint nowadays, that is strip seal. In this, you have a metallic extrusion of a specific shape. You have a very simple elastomeric seal like this, which can expand and contract, and at about 5,000 rupees a meter, it can take the loads. It can transfer or transit the structure. When you have a larger movement, now here the limitation is that this movement, plus and minus together due to expansion, contraction, temperature, shrinkage, heat, etc. If it's up to 80 millimeters, this is fine. Otherwise, you have to go for modular strip seal, which you can see the shape here. Each of them can take 80 millimeters movement, plus and minus added together. So finally, you require number of them as the length of the bridge is, which has to be bridged. In finger type, you have metallic fingers, as the name suggests, and they just bridge the gap. The vehicle can move over it without any problems. But the finger type expansion joint itself, being in metal, is a little prone to corrosion, etc. So we have to worry about those parts in terms of durability. We have box seal, wherein compression seal, wherein we have this kind of elastomeric box which can expand and contract. But looking at the shape itself, we can make out that this can't take very large movements. It can take movements plus and minus together only up to 40 millimeters. Now we talk of the reinforcement and pre-stressing. Reinforcement is passive reinforcement, whereas pre-stressing is active. Let me just check how many slides, because I should not be missing my slide. 60, okay, we have 5 more, fine. So I'll go to this. Okay, in pre-stressing what happens, you put some kind of a metallic cable running along the tensile bending moment profile and stress these cables and lock it to the structure to give compression where we have tension on account of the bending moment. Pointer options, laser, okay. So, let's say if it's a 2-span beam with the supports, you have tension here, so you provide the pre-stressing here. You have tension there, provide the pre-stressing. You have tension there, provide pre-stressing there. But for doing this, we provide ducts that look something like this, metallic ducts or rubber ducts, the plastic ducts, high-density polyethylene. And in the ducts, we place pre-stressing hardware. Hardware means, first of all, we have the duct, which is placed in the concrete while casting. And after that, we bring in these pre-stressing strands. Now here, you see, this is something called a cone. This is an anchorage cone, which looks something like this. And this is also placed till here. Concrete line is here. And after that, you put the pre-stressing cables. And then you put the bearing plate, we call it, which has conical holes. In the conical holes, we place this kind of conical wedges. And these wedges have serrations inside, like teeth inside, so that once we have stressed a cable and we have hammered these wedges, they start biting onto the strand to make sure that the strands don't go inside. And they hold the force onto the concrete. After that, we come and we grout all this with the cement so that it's permanently done and also protected against corrosion. Now, as regards to strands are concerned, strands comprise 7 wires, central wire and 6 outer wires, and this becomes a one strand. And when we have number of strands put together, it becomes a cable like that. So this is one more picture. I'll probably skip this. This is how it looks. Now, pre-stressing gives a reduced span to depth ratio, reduced deflections because the cracking is avoided. You have compression generated by the pre-stress, enhanced serviceability, therefore more durable and long-lasting concrete, reduced construction time because moment you pre-stress after 3-4 days, you can move your shutter in the case of cast in situ. You don't have to wait for 15 or 21 days, unlike a large span in situ cast in situ RCC game. And enhanced aesthetics because you have a slender structure due to pre-stressing. Okay, 1 or 2 more slides. Aesthetics. Now, nowadays, since the bridges or the flyovers are in the public limelight, they are in the urban areas, and we also want to see something which is aesthetically pleasing. A lot of thrust is going in making the structures pleasing. So if you look at this expressway, which is going from Bangalore to Silk Board Junction to Electronic City, 10 kilometer long. There we have provided rubber liner in the shutter while casting the precast segments to give this kind of a interesting shape to the segments. So when you see from below, you will see a better shape compared to just the plain concrete. So that's what we do, and thank you so much. I know I was rushing, but I have another 10 minutes at least before I go to security and all that. So now I leave it to Professor Jyoti Pusari.